today we'll talk about the properties of strongly pseudoconvex domain. Yeah, so let us recall the definition of pseudoconvexity. Let omega be a bounded C2 domain in Cn. Bounded C2 domain in Cn. Let rho be a defining function of omega and assume P is a boundary point of omega. Then P, the point P is said to be the point of pseudoconvexity. If the complex region of the Levy form del square rho by del z के बाद at P w के बाद is greater than or equal to 0 where j or k is from 1 to n where w is in complex tangent space. So let us recall what is TP10 omega. So this is all w in Cn such that del rho by del zj at z wj equal to 0 at P from j j is from 1 to n. Okay, so and we say P is a point of, so this we call Levy form. So the P is said to be strongly pseudoconvex convex point if this Levy form is positive definite or is positive for all W non-zero in TP1 in the complex tangent space. And we say omega is pseudoconvex if it is convex, pseudoconvex at all boundary point, and it is strongly pseudoconvex if it is a strongly pseudoconvex at its boundary point of omega. So yeah, so we say this omega is pseudoconvex. Similarly, say strongly pseudoconvex at all points of boundary omega are pseudoconvex or strongly pseudoconvex. Let us see some example, some quick example. Let me take omega 1, which is z is in C2 such that z1 square plus z2 square is statistically less than 1. So this is a ball in C2. So here you can check that this is strongly pseudoconvex. And the second one, if you take omega 2 is something like z in C2 such that z1 square plus z2 power 4 less than 1. So if you draw the diagram of this omega 2, so it's like if you draw in a Reinhardt ring, so this is same mod G1 and this is mod G2. Then this is something like this. So this is omega 2. So here you can check that this point is of pseudoconvexity, but this is not the point of strongly pseudoconvex, not strongly pseudoconvex. Okay, I think this is C1 and this is C2. You can check. So this is the example of pseudoconvex domain, but it is not strongly pseudoconvex. And the third one, so recall last time we proved that convex domain are pseudoconvex, but the pseudoconvex domain may not be convex. So we saw last time that in a domain C, any domain is a pseudoconvex domain. But now what about in C2? So in C2, can we give an example of domain which is pseudoconvex but not convex? So anyone has some example in mind? Okay, I will give. So if you consider say omega 3, say G in C2, that real part of Z2 is strictly greater than e power minus 1 by Z1 square. Then you can check that omega 2 intersection of 0 1 is pseudo-convex but not convex. Here you have to regularize this domain because this is not a C2 domain. So, but if you are, so omega 2 will be look like this. So like this is real part of Z2 and this is mod Z1. So it's something look like this. So the if you look at some near ball 01, then here the convexity will break, but it will remain pseudo convex on this domain. So this is V01. Okay. So also recall something from the last time. So last time we proved two things. So the first one, we proved convexity will imply pseudo convexity. And the converse is not true. We saw from the last example. And the second one, we proved that pseudo convexity is just uh, is invariant and isomorphism. So in lecture one, we have defined the convex domain, and in the lecture two, we defined this pseudo convexity. So can we say this convexity and pseudo convexity are related up to the biholomorphism? So what I'm saying is that assume this is domain omega and this point P is a point of pseudo convexity. So this is the point of pseudo convexity. And assume there is a biholomorphism phi. So this is U and phi is biholomorphic from U to phi U. So it will map something like some domain omega prime and say this is point Q and this is say your phi of U and phi of P is Q. So assume if we have a point P which is pseudoconvexity, can we say this point Q is a point of convexity, means the real convexity? So this was the conjecture. So I will write the conjecture first. So conjecture is saying if P is a point of pseudoconvexity, then the, yeah, then there exists a holomorphic change of coordinate such that, or maybe phi on a neighborhood of U of P such that this phi U intersection with this boundary omega is convex. So conjecture is basically saying that if P is a point of pseudoconvexity, then can we find the some biholomorphism phi such that this phi U intersection with boundary omega, basically this red line or the red boundary point is convex. So, but unfortunately, this conjecture is not true. So, this due to Kohn and Nirenberg, this conjecture is false. So they gave one example where you can't find any holomorphic change of coordinates such that if P is a pseudoconvexity and then the this boundary is not convex. But now we can ask for the strongly convex point. So this conjecture
So
is mhm.
I mean greater than one, right? The dimension of the space. I mean,
Yeah. So here everything is greater. Means we are talking about n greater than equal to 2 dimension.
okay, okay.
Okay, for n equal to 1. Okay, because every simply connected domain is biholomorphic to ball. Yeah, so maybe it's n greater than equal to 2. For n equal to 1, I don't know. You may think, but I don't know. Maybe for simply connect, if you remove some point from the domain, then it's not simply connected. Okay, but I feel like for a domain in C, it's true because, okay, for example, let omega subset of C, then you omega is something like this, and we are talking about the local thing. So if you take P in a boundary of omega, then you can always take a ball uh, such that so, means you can always take a neighborhood U of P such that omega intersection U is simply connected. If your domain is C2 smooth, then you always know you can find Riemann map phi such that this is biholomorphic to unit disk D, and you are in a good shape. So for
Yeah.
domain in C, this conjecture is true, I guess. So yeah, so Kohn and Nirenberg has some example which has dimension greater than or equal to 2. Okay, good point. Yeah. So now I am saying so here.
So this conjecture is
Mm-hmm.
false. So this conjecture is false.
If dimension is greater than or equal to 2, means
Oh,
the
so
domain is great containing Cn where n is greater than or equal to 2.
Acha, acha. So is there any new theory or something like that which says about
Mhm.
some, like, if we assume some condition, is there something like that? We,
Yeah, yeah. So there is a something like this what H extendable domain. So they assume some condition on a defining function, then they have proved that the up to the biholomorphism, the new domain will look nice, not
okay.
exactly convex, but it look nice, so that you can
We,
do your estimates.
so, like for
Mhm.
manifold, we know that there is a coordinate change such that we can make like
Mhm.
equal the domain as the
Mhm.
lower half space, something like that. So
Mhm. Yeah, bit boundary. Yeah.
yeah, so you
Yeah,
like
but that yeah, I agree. But that map may not be
holomorphic.
biolomorphic.
Right, right.
Yeah. Yeah. Otherwise, if you have manifold with boundary, you can always find a one chart such that it will map to upper half plane. But
Okay,
then that map may not preserve the pseudoconvexity because pseudoconvexity preserve if we have a biholomorphism.
okay, okay. So is there any anything like that key on the boundary on the P point if we find
Mhm.
the tangent space and uh like if the tangent space is
Uh,
complex or something like that? I'm not
uh,
sure. Like, is there anything some like that?
okay, yeah. So uh, I actually don't know if our just if we just assume pseudo. Yeah. So if you
Okay,
assume it's strongly pseudoconvex point, then due to Narasimha, they prove that there is a coordinate holomorphic coordinate such that the target domain is convex.
okay,
So So we'll give the proof, then you may get some idea. Can we have a more general case? Means if we have a point which is pseudoconvex but not strongly pseudoconvex, plus put some extra condition, can we have some this
okay, okay,
local holomorphic coordinate?
okay, okay, okay,
Yeah.
okay, okay,
So
carry on.
I will give first for strongly pseudoconvexity, then we can talk about the more general case. Yeah.
Okay, 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 sure.
Mhm. So then our next question is, what about if is a point of strongly pseudoconvex? So then the this so, yeah. So now basically I am saying that so this is omega, and say this is a point of strongly pseudoconvex, and this is a u. Can we find a biomorphism phi such that this so this is like phi of boundary omega intersection u is yeah. So sorry, let me erase. So this okay yeah. So this black one we are calling this phi of boundary omega intersection. So we are saying that can we find some phi such that this is convex or basically strongly convex. So this is the result due to Narasimha. I will state the result explicitly, but before that we need one lemma to prove this theorem. So let us write the lemma. It's saying that let omega be a bounded domain in Cn and it is a C2 smooth. Assume omega is strongly pseudoconvex. Then there exists a defining function rho tilde of omega such that this Levy form jk1 to n del square rho by del zc del zk bar wj wk bar is greater than equal to some constant times mod w square for all w in C. And here C is some constant or some positive constant. Okay. So let us recall. So when we have a strongly convex domain, then I have proved that there exists a rho tilde such that this type of estimate is true for real Hessian. Now I'm saying that if omega is strongly pseudoconvex, okay, this is for all p on a boundary omega. Then now I'm saying that if we have a strongly pseudoconvex domain, then we also find one defining function rho tilde says that this star is true for all p on boundary omega. So the proof of this lemma is exactly same as I was proved for strongly convex domain in lecture 1. So just replace the real tangent space to the complex tangent space and you will get this rho tilde. So idea of the proof is to choose this type of function. So rho lambda of x is equal to e power lambda rho of z minus 1 by lambda, where lambda is positive. So we have to choose lambda large enough so that this property star will true. Okay. Okay, but this lemma is a little bit weaker also. So let me rewrite again. Assume omega is strongly pseudoconvex at point P in a boundary omega. Then this Levy form is positive for that P in a boundary omega. So I will not prove, I have just given this idea. You have to take this rho lambda and do the same thing as we did in a strongly convex domain. You will prove, you can get this lemma. Okay, so now we'll move on to the main result. So the theorem due to Narasimha, let omega be a bounded domain in Cn. Here n is greater than equal to 2. Be a domain. C2 boundary. Let P in boundary of omega be a point of strongly pseudoconvexity. Then there exists a holomorphic coordinate. Then there is neighborhood U of P and biholomorphism phi
Ravi,
on.
your slide is not visible.
Okay. How can you see?
Yes, yes.
Okay. Yeah. So then I was stating this Narasimha theorem. So Narasimha theorem, it's saying that let omega be a domain with C2 boundary and let P be a point of strongly pseudoconvexity. Then there exists a neighborhood U of P and a biholomorphism phi on U such that phi U intersection with boundary omega is strongly convex. Yeah. So I have drawn the many times the picture. Okay, let me draw one more time. So this is the point P and this is omega and this is U. And can we find the phi such that this phi omega?
Again, it disconnected. I mean, your
Oh man,
slide is not visible.
okay. Yeah, now it's visible, right?
Yes, write something, then it will be clear.
Okay. Now,
Yes, yes, yeah. Now it's
yeah, I will complete quickly this proof. Yeah, so basically we have to find the phi such that this phi U intersection boundary omega is strongly convex. So let us give the proof. We have here P is a point of strongly pseudoconvexity and this is omega. So first we translate, then translate such that P will go to 0. So something like this. So P is on 0. And because translation is kind of biholomorphism, so if omega is strongly pseudoconvex, this new domain is also strongly pseudoconvex. So it has a say this is normal N of P. So now we will choose some unitary transformation such that this NP will go to E1. E1 means 100. Then this omega will look like, so there is a 0 and NP something like this is E1. So NP is the outward normal. Okay. And this unitary transformation is also a kind of biholomorphism. So we can say that omega, without loss of generality, omega, we have to just prove at point 0 with normal on E1. Because if we prove that there is a biholomorphic change of coordinate on this omega such that it is convex on the target domain, then you can just compose with translation and this unitary transformation. You will get the holomorphic coordinate for this point P. Okay, so it's enough to work with this domain omega. Okay, so let it has a, so this omega is strongly convex, is strongly pseudo-convex because this omega is strongly pseudo-convex and translation and unitary transformation both are biholomorphism. So then by previous lemma, there exists a rho tilde such that jk1 to n del square rho tilde by del zc del z के बाद. So here the boundary point is 0. Xi से xi के बाद is strictly greater than c times mod xi square for all xi in CM. and C is some non-zero constant, or C is some positive constant. Okay, so let us write because we know rho tilde is a C2 function because our domain is C2. So let us write the Taylor series. So if you write the Taylor series near zero, it will be rho tilde of Z. Let's write W here. So this is rho tilde of zero. So I'm writing this Taylor series in a complex form. So this is 2 times real part of JK 1 to n del square rho by del ZK del ZK at 0 WJ WK and there is a 1 order term J from 1 to n del rho by del ZK at 0 WJ plus 1 Levy form del square rho del ZK bar at 0 WJ WK bar plus little o of mod W square. So little o of mod W square means, so this means basically if you divide by mod W square, this will go to 0 as W goes to 0. And this Taylor series, if you write in a real coordinate and if you change in a complex coordinate, you will get this type of Taylor series. So this is by Taylor series. Now we also know that 0 is a point of boundary omega, so this is 0. And also because we know that NP is E1, 1, 0, 0. And this is basically gradient of rho tilde at 0. So from this thing you will get del rho tilde by del z1 at 0 is 1 and del rho tilde by del zj at 0 is 0 for all j from 2 to n. Okay, now if you put this thing in the Taylor series, you will get rho tilde of w 2 times real part of. Okay, I think in a Taylor series there is a no 2. Let me just. We will basically get. So from here you will just have a W1 plus JK 1 to n del square rho by del ZK at 0 WC WK plus this Levy form JK 1 to n del square rho del ZK bar at 0 WC. Okay, this is WK. WC WK bar little o of mod W square. Yeah, so we'll get this thing. So now we have to take a biholomorphic coordinate that the new defining function has just this form because we know this is positive. This is rho tilde because we know rho tilde is this omega is strongest pseudoconvex domains. So this thing is always positive. So we'll take phi something like, so we define phi something like this. So in a new coordinate set W, so we take phi w is w prime, where w prime is w1 to wn prime, and we define this w1 prime is this whole thing. It is like a w1 plus. I will define this, then it will be clear why I am defining this type of phi. 1 to n del square root tilde del zj del zk at 0 wj wk, and other than that you just define wj prime wj for j 2 to n. So here it is not guaranteed that this phi is a biholomorphism, but if you take the Jacobian of this phi at 0, this is non-zero. This you can check because our function is simple. You can differentiate, and at 0 you will get just the some identity map. So which is, so that means its determinant is non-zero. So now you can imply the inverse function theorem. So by inverse function theorem, there exists a neighborhood W of 0 such that phi from W to phi W is a biholomorphic map. Yeah. So what we basically did, so here is our omega and this point is 0. So we said there exists a neighborhood W such that in a new coordinate, so say this is a coordinate W and this is a coordinate W prime, and say this is omega prime. So on W we know this phi is a biholomorphism, and note that this phi 0 will be 0 because that's how we define our phi. So this is a point 0. So this is a phi, and this is phi of 2. So we get the biholomorphism phi. So now we have to prove that this boundary point is a point of a strongly convex domain. So here we know it has a defining function rho tilde. So here you can check it. This domain has a defining function rho tilde composed with phi inverse. So say this is rho hat. So this rho hat is a defining function of phi omega phi w intersection with omega prime. Okay. So if you write, so now we have to prove that this omega prime is strongly convex. That means if we can prove that the real Hessian of rho tilde rho hat is positive, then we are done. So now we have to rigorously find what is the formula of rho hat. So let us see. So rho hat of W prime is nothing but rho compose phi inverse of W prime. And note that from here phi W is W prime. So here phi W is W prime. So that means this is rho hat of W because phi is a automorphism because our W prime is in phi of W. So here everything is biholomorphism, so you can do that. And rho hat of W we know from equation say this double star. So if you put rho hat of W and we know this thing is nothing but W1 prime because that's how we choose. So rho hat of W is nothing but real part of W1 prime plus the other coordinate I will write just like that. Same JK1 to n del square root by del ZC del ZK bar at 0 WC WK bar plus little of mod W square. So here we have to write this thing as a function of W prime, because here I am taking rho tilde as a domain with respect to W prime, or the coordinate with respect to W prime. So note that since phi is a biholomorphism, so you can compare W and W prime. So because phi is a here biholomorphism, that means phi and phi inverse both are uniformly continuous, or say both are Lipschitz function on some smaller neighborhood near zero. So from there you can see that mod W is same as mod W prime. This means mod W is less than C1 times W prime, and also mod W prime is less than or equal to C2 times mod W. This you can check because of Lipschitzness of phi. Okay, and phi 0 is 0. Otherwise you may not get this thing. So yeah, so now if you again write rho hat of W prime, means mod W is same as mod W prime, you can write the real part of W prime plus JK 1 to n del square root at 0 ZC ZK bar. This is O tilde. So here this W1 is, so basically W1 is equal to W1 prime plus some little o of, or the big O of capital W square, or big O of mod W square. So you can check, I have said this is exactly WJ prime WK prime plus little o of W prime whole square. So this you can check using this thing. It is easy. Okay. So once we have this defining function, then because this is Taylor series near zero, so here you can see that the real region of rho tilde at zero is exactly this thing. JK 1 to n del square root tilde 0 by del zk bar of wj wk bar with prime. And we know this is strictly positive because our domain is strongly pseudoconvex. So from here we get that the point 0 is a point of strongly convex domain or strongly convexity. Okay, so what we did basically, so this is omega and this is a point P, and this is, we get some neighborhood W such that up to a biholomorphism, this point 0, and say this is phi of omega. This 0 is a point of strongly pseudoconvexity. But okay, you can check that this strongly pseudoconvexity is a open condition. Open condition means if the point zero is a point of strongly pseudoconvexity, then you can find a small neighborhood near zero say V such that this all the points here are strongly pseudoconvex. So if you take our U is phi inverse of V, then you can see that this phi of U intersection with boundary omega is a point of strongly convex. Strongly convex. Uh, then you can see that phi U intersection V is strongly convex. So this will prove the theorem. I hope the proof of the theorem is clear. So it's basically you have to play with the defining function and with the Taylor series of the defining function to get this theorem. So now one exercise to think, which I think Viplo or someone asked. So fine. So let omega is a domain in, or say pseudo-convex in Cn of n is greater than equal to 2. So in a conjecture we saw that if we just P is a point of pseudo-convexity, then we can't accept up to a holomorphic coordinate that point the target point is a point of pseudo-convexity, is a point of convexity. So now I am saying assume so this is U. Boundary omega intersection U is pseudo-convex. Okay. Then we get holomorphic coordinate and that holomorphic coordinate say phi such that phi U intersection boundary omega is convex. Yeah. So this is the exercise you can think about it. Yeah, that's all what I have to say. Thank you for the attention. Yeah, if you have any doubt, you can ask in the previous story or any other.
Do we have any question? Okay, so if
Yeah.
not, please.
Yeah, I have one question.
Yeah,
So, I heard there is a definition of strongly pseudo-convexity even if the domain is not C2 boundary. So,
Yeah.
Narasimha's theorem, like some kind of that theorem, is it like is there or something like that?
Okay, so you are saying if the Narasimha theorem is true, if we have a lower regularity, not C2.
Yeah.
Yeah, but okay, for that we need the target domain. We need it is strongly convex, right? Okay, so here we define the strongly convex domain using the C2 domain. So before that, we have to make sense of strongly convex domain which has a lower regularity. Okay, so it's actually a good question. Means I don't know because I have always worked on a C2 domain and higher. So I don't know if we reduce the regularity, there may be some result, but I don't know. Okay,
Okay.
or if I had some, or I will look at it. If I have something, I will let you know.
Okay, sure. No problem.
Yeah. but I think there may be some result.
Okay. And about the exercise, is it? I think it is
Mhm.
false. Is it? Like there might.
I'm not sure. It is. It should be false, but I'm not sure because I
Okay.
also don't know. I also think about it.
Okay.
Yeah, because if you see the proof of this strongly convex domain, here
Ah,
we are basically using the fact this
it is
is
strictly greater than 0, yes.
strictly greater than zero for all W, means
Right.
not in a complex tangent space. So if we have to prove for convex case, we have to take care of this WJs also, which I don't know if we can take care of or not.
Okay. So when we convert this to real Hessian, then something might happen. Like
Yeah. If we try the same proof and if we can see that if the complex tangent space we have nicely under this biolomorphism file, then it may be true. Otherwise, we can find some counter example.
I think
okay.
that is false even one dimension.
Yeah, positive forward nation. That is
No. For one dimension, you can always find right some locally simply connected domain which is biolomorphic to ball,
by
and
real
ball is
numbers.
always convex because
I
it's
see.
just a local condition.
Right.
Yeah, but for CN, I think it may be false, but I don't know any reference or any example.
So the result, like phi of
Mhm,
omega intersection boundary of omega is strictly
mhm,
strictly convex. Is it
mhm.
equivalent to saying that phi of omega intersection U is strictly convex?
That we proved right from the last term, right? If one point is strongly convex,
Hmm.
strongly pseudo-convex, then we can always find holomorphic coordinate such
Hmm.
that phi omega boundary omega intersection U is strongly convex. So
No,
let's
I'm saying boundary
okay.
omega intersection U is strictly convex. Is
Oh,
it
convex.
equivalent to that boundary of not boundary, like omega intersection U is strictly convex?
Okay. So you are something saying. Okay, let me write. So this is omega. You are saying this is U and saying this thing is
Hmm.
strongly convex.
Yeah, I was
Then you are
saying,
basically saying that
hmm,
omega intersection U is strongly convex.
yeah,
Yeah,
is it
it is
equivalent
true.
something?
Yeah, it is true if U is convex or U is strongly convex.
Okay.
Because assume U is something like this. Okay, let me draw. So like U is this.
Got it.
Then you can see that this is not convex. Yeah,
Right.
so if U is strongly convex, then you can say that.
Okay.
Yeah.
Maybe that will like reduce,
Mhm.
that will help. That might help like sometime
Yeah, it may help, but
seeing the ball.
yeah, if we study some local property, then U in our hand, we can just take U as a ball. Means if
Okay.
we talking about just local condition, yeah, if we have a global condition, then you can take U is whatever you want.
Okay. Or I was asking like, can we find
Mhm.
such U such that U intersection omega is strictly convex or not?
Yeah, you can take U as a ball,
Acha, okay.
yeah, or some strongly
Okay.
convex domain. Yeah.
Okay.
Ravi,
Mhm.
uh,
Yeah.
so regarding this exercise, how did you
Mhm.
say, like, what was your reason to say that it is true in one dimension?
Okay. So like omega is here, same subset of C,
Yeah.
and say this is okay in any domain in C, all the points is pseudo-convex. That we saw earlier.
Can you just go to that exercise?
Okay.
But Ravi, that example, how does that work for annulus?
Yeah,
Which
actually,
example?
also the thing, because here we are taking U intersection the boundary of omega, so we are getting the curve of
Yeah.
the boundary only. So to make it a
Uh-huh.
convex image, so make it as a image of this one as a convex, we have to make it a straight line. That is not always possible, I guess.
No. So say this is a point P, right? if you take say annulus, so something like Agniva said, say this is annulus in C.
Mhm.
Take any point P in a boundary omega. So we can take a small enough neighborhood such that this, so if say this domain is omega and say this is U. So we can always find omega intersection U which is simply connected, right?
Yeah, that is fine. Omega
Yeah.
intersection U is simply connected.
So now we
But
have a Riemann map.
Mhm.
Phi says that this phi of U is a disk and the boundary point is something like this. Say, or I'm missing something. Let's say.
yeah, what is the boundary point here?
Okay, so the boundary point is something like phi of boundary omega intersection with U.
Phi of boundary of omega intersection U. Yeah, so this is
Okay,
so this may not be
yeah, yeah,
convex.
yeah.
This may
Now I
not be
got it.
convex.
Yeah,
Yeah, yeah.
correct, correct.
But to
It
make
may
it, we
not
have
be
to make
convex.
it a straight line only.
Yeah, yeah.
Acha,
So
can
whatever, yeah, whatever I said, I'm taking back. Yeah, it may not be convex.
Yeah,
So
that's
you may get some example, counter example in C also. If
it
P
Acha,
will
is a
behave
maybe
point of,
like a
can you do like
domain.
that? Like
Mhm,
if we take U intersection omega, just U
mhm.
intersection omega, that is simply connected. So that we can by some Riemann map we can send U intersection omega to lower half of the disk, right? Then if we
Oh,
somehow
sorry,
extend it,
sorry, I got confused. Yeah, I think you will get convex now because
Okay, okay,
our
yeah, we
simply
can move
connected
to
is
upper
this.
half. We can.
Yeah, our simply connected domain is this now. Phi omega intersection U. So I'm mapping this to unit disk.
Mm-hmm.
Okay, let me write again. So this is phi of omega intersection with U. And we can also assume that we can also take U such that this omega intersection U is at least C2 domain. We can just take U nice
Yeah,
enough
now I
such
understand.
that omega intersection U is C2.
Yeah,
Then
now.
our domain is C2, then phi is also smoothly extended. So like
Mhm.
this point is 0 and phi will smoothly extended. So you can see this point is point of strongly convex or point is convex, right?
Acha, can you repeat?
No,
I
no,
didn't get it.
but if a simply
Uh-huh.
connected domain is not if the boundary of simply connected domain is not
Mhm.
locally connected, we won't be
No,
able
no,
to get
no.
such.
I agree, but our domain is here C2, right? So we can
Oh, you are
always
taking
take.
already C2 smooth. Okay, yeah,
Huh,
fine. Yeah,
I'm
then
I'm just taking the smooth domain, not the
fine.
yeah
Yeah, then it is fine.
yeah yeah. In our lecture or in my lecture, everything is C2.
Yeah, yeah, fine.
Yeah, then we can take Riemann map, and if our domain is C2, then it is also extend up to the closure,
Yeah,
and then you can see that this point is
yeah.
convex.
I think the
Yeah.
better way to say this would be
Mhm,
that the intersection part, like omega intersection U, this can be
mhm.
mapped biholomorphically to the upper half plane so that the boundary will
Okay.
be contained in the real line so that convexity will be visible easily. Yeah.
Yeah, but unit disk is also convex. Okay.
Yeah. Okay.
Means the Riemann map is more famous. I think that's okay. Yeah, or whatever. Both are true.
Hmm.
Yeah. So the problem is basically in higher dimension.
Yeah, but in higher dimension also to state this problem. Okay.
Mhm.
Okay. Anyway, yeah, biholomorphic map will extend smoothly. Yeah. Fine.
Yeah. But we don't have Riemann map, right? So
Yeah. Yeah.
that is the difference
Yeah.
between
Yeah. Yeah, understood.
one and multivariable. Yeah. Okay.
Okay. Any other question? Okay. So if not, let us thank the speaker. Thank you, Ravi.